Thanks very much. Good afternoon, everyone. Thanks for the opportunity to come and talk to you. I don't have anything to declare in terms of financial interests. So I took the title I was given fairly literally, so I'm going to spend a bit of time telling you about what magnetic susceptibility is. I'll talk a bit about how we can measure magnetic susceptibility, and then I'll spend some time looking at how we can validate methods for measuring magnetic susceptibility, and also say a bit about what is the ground truth in tissue when we think about susceptibility. So from the start, magnetic susceptibility, chi, is the thing that characterizes the magnetic properties of matter. So it's essentially the proportionality constant that links the induced magnetization to the applied magnetic field. And there are actually two magnetic fields when we think about electromagnetics. So it's the magnetic induction B, which actually dictates the NMR frequency, which is what we care about usually in MRI and NMR. And that's sort of made up of a combination of the effects of the applied field and the induced magnetization. So as you think we've heard already, susceptibility can be negative or positive. A negative susceptibility corresponds to diamagnetism. Positive corresponds to paramagnetism or ferromagnetism. So we have an area of empty space, we apply a magnetic field, then if we put some material inside that magnetic field, the field is perturbed. If we have a diamagnetic material, that object will kind of expel the magnetic field, will reduce the field inside it and a bit around it. And if you have a paramagnetic object, it will enhance the magnetic field. And that's because there's an induced magnetization in the material. The magnetic field that magnetization produces either acts against or with the applied field. So when we think about these kind of materials, maybe moving towards the context of MRI or NMR, ferromagnetic materials, which I haven't mentioned, they're materials which have large positive susceptibility values, and they can become magnetized, remain magnetized even when magnetic fields are removed. We don't normally bring them into the environment of an MRI scanner, so we don't have to worry too much about them. Diamagnetic materials, everything is intrinsically diamagnetic. When we're thinking about living systems, aqueous samples, they generally have small negative susceptibility values, around about minus 9 parts per million for water. And then paramagnetic materials are materials which contain intrinsically material which gives individual magnetic moments which statistically line up with the field. And we're thinking about the context of MRI. It's often things containing iron like deoxyhemoglobin which give rise to paramagnetic effects. So if we look across the whole spectrum of materials, you can have a pretty wide range of susceptibility values, but focusing in on what's mainly relevant for MRI, we're sort of mainly interested in what's going on around the susceptibility of water, which is minus 9 parts per million, but also we're interested in the relationship to the susceptibility of air, which is close to 0. So when we think about looking around water, it's typically things which are a bit denser, there's a bit more material there, which have a more diamagnetic, a more negative susceptibility, like maybe hard bone or calcifications. And then when you think about things which contain paramagnetic material, usually iron-containing compounds, but also contrast agents or molecular oxygen, the more of those you add to the aqueous system, the more paramagnetic it becomes. So it's worthwhile in a session, I guess, linking to standards a bit and thinking about good numbers. Then there are multiple definitions of the magnetic susceptibility. What we've been looking at so far is the volume magnetic susceptibility. You can also define the mass susceptibility, susceptibility per unit mass, or the molar susceptibility, the susceptibility per mole of a material. But all of those measures are very simply related. A slight complication, if you look in the literature, is that even today, susceptibility values are quite often quoted in CGS units rather than SI, and there's a rather arbitrary factor of 4 pi, which takes you from CGS to SI. So you multiply by 4 pi to go between the two. So when we're thinking about the human body, and this is a first example, quantitative susceptibility map, then the dominant feature really that you see is the effect of iron deposits. So non-heme iron deposited in the form mainly of ferritin. So if you compare with a brain section which has been stained for iron, then you see these sort of bright regions correspond to the dark regions here, the deep grey nuclei, the putamen, the caudate and the globus pallidus, which contain a lot of iron, and they appear bright in the susceptibility map. But we also actually see quite a strong negative contribution, relatively negative contribution, which comes from the effects of myelin. So we see that in mainly the large tracts, as we see here, the corpus callosum and the octitracts there. And that's, correspondingly, we see those structures in a myelin-stained brain section. If we're thinking about where there's pathology, we also see quite strongly the effects of blood products related to a bleed, which are highly paramagnetic, and hemosiderin in particular. And we can also see the effects of calcifications, which are more diamagnetic than the surrounding tissue. So one application of QSM has been to differentiate between calcification and bleed in the brain. They appear similar in a CT, but they appear with opposite sign in a QSM image, and they maybe appear similar in a T2 star-weighted MRI as well. And of course, if we move into the body, then an area of interest is looking at the liver, and it's the liver iron content which actually drives quite significantly the susceptibility. It's just worth mentioning, though, that there's a sort of complication that we gloss over sometimes, and that is that at the molecular level, magnetic susceptibility is actually anisotropic. So it means the induced magnetization depends on the orientation of the molecular structure with respect to the applied field. The simplest example is a benzene ring to illustrate this. So if you have a magnetic field applied perpendicular to the benzene ring, it's easy to induce changes in the electronic currents in the ring, which which generate a magnetic field which opposes the applied field, and therefore you get quite a strong diamagnetism. If the ring is oriented parallel to the field, you don't get that effect on the currents, and therefore you have a different susceptibility. And this sort of effect can actually transfer over, it transfers over to other larger molecules, to alkynes, and also to protein alpha helixes, and most importantly, it transfers over to the lipid chains in the myelin sheath, which are very many of them are found within white matter, and it's an area where it adds a bit of complexity in the quest for the ground truth, and it's particularly important in white matter, and I'll just come back to that towards the end. So how can we measure the magnetic susceptibility? Well, you may, as a physics experiment in the past, have used one of these, a GUI balance, where you take a piece of material, you put it into a region where some of it's in one magnetic field, some of it's in another, and you essentially weigh it. You measure the change in weight in the presence of the field, and then you can measure bulk susceptibility. Something like the squid magnetometry we heard, where you have a vibrating sample in a magnetic field, and you pick up the changing magnetic field produced by the sample itself. So they're techniques that you can use for bulk samples or small pieces of sample, but with MRI, we need some way of measuring susceptibility, and the way to do that is to sense the change in magnetic field, which is produced by the induced magnetization. Particularly in MRI, we can measure the change in the component of the magnetic field along the applied magnetic field with incredible accuracy, in part why susceptibility measurements with NMR are so good. Obviously, we have complicated structures, so if we're going to get complicated field variations, we need some way of relating those field variations to the distribution of magnetic susceptibility. We can do that because we know what the magnetic field is from each little piece of magnetization. It will follow the common dipolar field pattern. So we have a distribution of magnetization. We can work out what the field pattern will be by convolving the dipole field with the distribution of magnetization. That's relatively easy to do. But in many situations, the induced magnetization is proportional to the susceptibility, just depending on the applied magnetic field. So it means we can get the field perturbation by convolving the susceptibility with the dipolar field. Convolutions, maybe not so easy always to computationally to carry out. So things always with Fourier transformation, convolutions turn into multiplications. So it means that you have quite a simple relationship in the Fourier domain between the magnetic field and the susceptibility, which is that you just multiply the Fourier transform of the object's susceptibility distribution with a kind of filter function. So we can estimate fields if we know what the susceptibility distribution is. So how can we now measure those induced field variations? Well, we're very sensitive to those field variations because the big value of the magnetogyric ratio, nearly 3 times 10 to the 8 for the proton, which means that as the magnetization processes, its rate of precession is very sensitive to the local magnetic field, and it will accrue a phase over time, and that phase depends on the local field. So we look at one region here, we'll get a phase accrual which depends on this positive field. In the negative field, the phase accrues in the opposite direction. In a zero field region, there's no accrual, and that phase accrual continues as time goes on. So by measuring the phase, we can say something about the local magnetic field. So how do we measure the phase? Well, we can map the phase very easily with a gradient echo sequence like this. Normally, we just worry about the magnitude signal and how it decays with the echo time, but the phase of the signal depends on the local magnetic field. So we can map the phase of the signal, we can map something that tells us about the magnetic field. An issue is, if we're trying to get to the ground truth of what the field perturbation is, that often there are other sources of phase variation present in the data, maybe due to RF interactions with the object or due to sequence imperfections. So to measure this value accurately, we need to have at least 2 measurements of the phase at 2 different echo times. So we can do that by measuring 2 echoes under a gradient, or we can measure multiple echoes, many more than 2. We can do that by applying a bipolar gradient like this to generate 2 echoes, or we could use a unipolar gradient. Often that's a better way to do that when you want to avoid effects of gradient imperfections. So there are a couple of other things we need to do in order to get to the field variation that came from the susceptibility in the region we're interested in. And I'm not going to go into these in great detail because you can give a whole educational talk on these, and hopefully there were good talks in those areas early in the week. But you need to unwrap the phase and you need to remove the background field. So just briefly, if you look at a phase map on the scanner, this is what it looks like. It has these sort of sharp bands appearing in it where the phase abruptly changes. And the reason you get those is that you measure the phase by taking the arctangent of the ratio of the imaginary signal to the real signal, essentially finding the argument of the angle of the complex signal. The problem is this is only defined modulo 2 pi. So as we look at the field, the phase changing, as we move along a line like this, then when we reach a value where the phase is minus pi, it just gets wrapped back into roughly plus pi. So we have a discontinuity. We can get rid of that if we just realize we have a discontinuity and we need to have a continuous phase, and we know that the wraps happen in this modulo 2 pi regime. So there are a whole load of different ways of unwrapping the phase, which generally work pretty well. And there are Fourier methods which have been applied here to reveal the underlying field variation. Once you do that, you see that what you see is not really linked so much to the local tissue properties. It's much more linked to the air-tissue interfaces. So we need to get rid of those sort of effects. So we need somehow to separate the fields we're interested in, which are coming from the susceptibility in the region of interest, from fields coming from external boundaries or other sources, because we only want to use that one to infer what the susceptibility is. So we need to filter out the external field. Fortunately, these 2 kinds of fields have quite different characteristics. In particular, the spatial variation of the internal field tends to be quite quick, whereas it's slowly varying for the externally generated fields. You have the property that the fields generated by external sources are actually harmonic in the region of interest. They satisfy Laplace's equation, and the two fields are kind of orthogonal to one another, except maybe right at the boundary. So you can separate them. Again, there are a whole load of different approaches for doing this, which I'm not going to try and describe. There's a great review of these methods, which is published in a recent special issue of NMR in Biomedicine. But if you run through that process, then you can unwrap the phase that you measure, you can get rid of the large-scale field variation from background fields, and you're left with something that just depends on the local susceptibility effects. So how do you then get to the susceptibility? Well, we know how to relate the field to the susceptibility, but if we just flip that round, we just can get the susceptibility in terms of the field variation just by rearranging that equation. But there are a few hidden issues here, well, not very hidden. The first is that this term on the bottom goes to 0 at two conical surfaces in K-space, and that gives you a problem. And also, if we want to do a Fourier relationship, we really need to know the field variation everywhere, but we only know the field where we have an NMR signal, so we can only measure the field variation inside the brain. So again, there are lots of approaches to solving these issues. Just briefly go over those and how the problems arise. So this problem of divide by 0, if you look at this function, which we can call the dipolar kernel in the Fourier domain, the problem is that it goes to 0 on two conical surfaces, which make the magic angle 54.7 degrees to the z-axis. And so if we have a uniform noise distribution, it's a bit of an assumption, but let's just go with it for the minute, then if that's in the measured Fourier transform of the field, then if we divide by this function, we're going to massively amplify the noise around the conical surface, so that's bad. So a simple solution is just to threshold out the maximum value of 1 over this function, so we don't multiply everything up too much. So we sort of take care differently about the way the field is varying in the Fourier domain around this conical surface. So if we do that and we take a threshold of, say, 1 over 100, then the maximum value of this 1 over the dipolar kernel goes up to around about 100, whereas if we threshold to 1 over 10, then we end up with a value just going up to 10. And so by applying this approach, we can upweight or downweight the effect of the noise. So I bring this in partly, so this shows now a susceptibility phantom used to test out this approach. So here it's iron oxide loaded pieces of agar embedded within a spherical phantom of agar, and then we can use that to test out the process in generating the susceptibility map and see the effect of varying this thresholding. Perhaps the sort of gold standard for susceptibility mapping on the scanner is what's called the Cosmos approach, which is an approach where we make measurements with the object, usually the head, at multiple angles to the field. And if you think about that, that rotates this conical surface relative to the Fourier transform of the susceptibility distribution, and it means we have less problematic areas. So we have 3 angles of rotation, we can actually have no problematic areas at all. But rather than doing a simple division, nowadays there are much more modern numerical approaches where we'll try and minimize the deviation of the measured field from an estimate of the field based on a current numerical estimate of the susceptibility. You can do that for multiple angles. You can also weight the signal to allow for the signal-to-noise variation in the phase data. You can force all of the susceptibility to be inside the region of interest, so that's a useful thing. And you can also, of course, bring in other constraints, like not allowing the susceptibility to change except in areas where the magnitude of the signal changes. So with a full sort of numerical arsenal, you can bring in lots of other constraints. You can use other kinds of terms in the minimization. You can use an L1 minimization rather than L2 minimization, and you can obviously make nice susceptibility maps from data measured at just one orientation. And you can make then nice maps of the whole brain in particular, which tell you about the susceptibility distribution. So there are a whole road of approaches available for calculation of the susceptibility from the measured magnetic field or measured phase initially. But I think it's fair to say that the field is still evolving and we haven't settled on a single standard approach yet. So there are packages available if you're new to the field. You know, there's the package from Mehdi from Cornell, there's the STI suite package, which from Jun Lei in Berkeley, and there are some nice resources also on GitHub where people have put together many of the available software packages around. So these are useful places to go. And of course, deep learning is beginning to be applied in this area. So it's a moving target, and being able to test these different approaches and how they behave on data is very important. So a couple of points, it's sort of general points about these packages, is to bear in mind that the measurements of magnetic susceptibility we make are always relative measurements of susceptibility. So there are two things sort of underlying it. The first is that the frequency offsets that we measure, which come from the phase offsets, essentially they depend on the arbitrary setting of a reference frequency on the scanner. The frequency we use for demodulation is probably set based on a measurement from a region of the object, maybe a slice, maybe a volume, and that's variable. So there's not a sort of absolute measurement of the frequency in this case. And also the dipolar kernel that we use in division is undefined at k is 0. So we can't have a setting of the accurate setting of the average value of the susceptibility. We normally set it just to 0. So what we're doing is forcing the average value of the calculated susceptibility to be 0. So we can just use that as our reference. We say we'll always force the whole brain susceptibility to be 0, or we could choose a reference region, say CSF, and pick out the CSF, find the average value there, and then measure everything relative to that. There's some difficulties in doing that in CSF because you have structures within CSF that can have different susceptibility, like the choroid plexus. But it's still an interesting ongoing discussion. There are some nice papers. There's a recent paper looking at the effect of using a range of different regions for susceptibility referencing. So how can we validate these methods for measuring magnetic susceptibility? Well, here are a few ways. We could use digital phantoms, physical phantoms, we can do reproducibility or repeatability studies, and maybe we can make comparison to gold standard methods. So here's an example, a sort of simple, early example of segmentation of the substantia nigra and the red nuclei, which we use then to do a forward field calculation. And then we could then embed that structure in a brain model, work out the sort of typical size of background fields for this region, and then we could use that to test the capability of background field removal methods, because we knew, in this case, the ground truth, because we'd simulated the field variation. That's a real data set for comparison. So with this sort of approach, you can test the efficacy of background field removal methods, you can test the efficacy of susceptibility calculations. And later in the session, there'll be a much more example of a much more sophisticated digital phantom, which forms the basis of the QSM challenge number 2 that we'll hear about. So we can also use physical phantoms. I showed you that example of using an iron oxide-based contrast agent embedded in agar within an undoped agar sphere. That's quite a nice way to do it, in that the relatively large iron oxide particles won't diffuse very far, so you don't have to have any boundary between you don't have to have any container for the doped samples. You can have a structure where everything gives you a signal. A nice recent example is this phantom, which was, I think, the project instigated by the Cornell group. So it's a phantom which contains 5 latex balloons which are filled with gadolinium, contrast agent, Magnavist in this case. And they could then embed that in agar, and it's quite a reproducible phantom. I think they made 5 of these and sent it around different sites. As was pointed out in the previous presentation, it's worth bearing in mind that paramagnetic materials have a temperature-dependent susceptibility. The diamagnetic susceptibility tends to be not so temperature-sensitive, except through variations in density. So they're able to use this phantom on a range of different sites to look at reproducibility of measurements. You can also do measurements on, with a phantom, which is a person, I suppose, essentially. So if you want to get a more complex system, so this example of a study from the Jena group, they looked at 8 subjects who were scanned 4 times on the same 3 Tesla scanner, and they were able to characterize, in this case, I think the repeatability coefficient in parts per billion for measurements of susceptibility from different areas, giving an idea of the confidence level of measurements. And there's a larger scale sub-study that was recently carried out in China, 2 subjects going around 10 sites, and then they were able to make detailed assessments of the reproducibility of susceptibility methods. So later in the preferred papers, there'll be a talk about a 10 subject study at 7T. Okay, so we could try and make comparison to gold standard methods, but that's kind of difficult because these are measurements on samples. You know, you can maybe make a head size system, vibrating magnetometer, but it's going to be a difficult one to do. So there isn't really an alternative in vivo measure that I'm aware of. So one way is to say that we have a gold standard, which is the Cosmos data, and to make comparisons to that, or to, I haven't talked about this, but to some of you may be aware, the STI approach. And that was the basis of the first QSM challenge, which was a very successful piece of work, which was described in a paper, and there's some nice data that you can look at if you're interested in testing your method out. You can get further by making comparisons with post-mortem tissue, maybe not so much with the susceptibility, but perhaps with the elemental concentration, as was done with this study with looking at ICP, inductively coupled plasma mass spectrometry. So just to close, a bit about what is the ground truth for susceptibility in tissue. If you think about it, the value of the susceptibility depends on the length scale at which you measure, atom, molecule, cell, tissue, and organ. And at the length scale of an MRI voxel, there's a very complicated distribution. To find the susceptibility, we use the phase of the sum of the NMR signal. So we sum the signal over the voxel, and then we find the phase from that. But voxels may contain multiple compartments, and it turns out that the phase that we measure in this way is not necessarily reflective of the average field or of the average susceptibility. So if you think about something like myelin, if you have a reasonable echo time, you're losing the signal from the myelin sheath. So you're losing the signal from one compartment. You don't see the effect of that susceptibility directly in this. You don't see the effect in that compartment. So fortunately, things work out okay in the circumstance where you have disordered samples or where motional averaging saves you. But it's worth saying that there are some other effects which can confound you, including exchange and susceptibility anisotropy. And then the final, one of the later presentations in this session will look at the effect of exchange on and how you might separate it out from susceptibility effects. So just to finish, I think hopefully I've given you at least answers at some level to these different questions, and thank you very much for listening to me.